Now I want to look at a couple of properties that we can use to determine series convergence or divergence. In this case, I guess specifically convergence. We've got two properties here about convergent series. So we start off by saying, say we have these two series, a series of ANs that add up to some big A, and a series of BNs that add up to some big B. Then the first statement is just saying that the sum of the sum or difference of terms is just the sum or difference of that overall sum. Another way to think of that is that you can break a series up. You could rethink of number one there as saying that you could break it up into two series, right? Because that's what this is equals to A and that equals to B. So, so you may know how to deal with those two pieces separately, but not together. So it's saying that you're welcome to break it apart if you like, as long as they're both convergent, then it's true. And then the second one just says you can take a constant out, right? If each term is multiplied by some k, then the overall sum is just k times the overall sum of the original. Again, another way to think of that is it's saying that you could bring that k out. Think of it as, we already know that's true for finite sums, right? If you've got that's really a common factor, right? You can take the common factor out of the sum. Well, it's also true for infinite sums as well. So both those things are nice. Let's look at an example of where we might use this. Say we had a series 3 to the n plus 4 to the n over 5 to the n, and from 0 to infinity. So of the stuff we've looked at so far, that looks a lot like a geometric series, right? Everything's to the nth power. But that plus messes things up, right? Because every time n goes up by 1, the bottom just gets multiplied by 5, right? Because it goes up 1 degree, so the bottom is just multiplied by 5. But both those go up by 1, and I can't factor that out because they're different, and they're being added. So together, they're not a geometric, but separately they are, right? If I look at the series 3 to the n over 5 to the n, that's geometric. And it converges because the absolute value of r is the absolute value of 3/5, which is less than 1. And the other series, 4 to the n over 5 to the n, also convergent geo, because the absolute value of r is absolute value of 4/5, which is less than 1. So we've got two convergent series. So, and there's no real theorem to quote here. It's just a property of series. So all you have to say is that because those two pieces converge, we know this series converges. Now we could even go a step further. Because they're geometric, we know what this adds up to, and we know what this adds up to. And the theorem tells us that it adds up to this thing is going to add up to the sum of those two. So let's go ahead and add that in there while we're at it. What does it converge to? Well, the first one, remember a over 1 minus r. Remember, a is just the first term. So in this series, when n is 0, you get 3 to the 0 over 5 to the 0, which is just 1. So in that first series, a is 1 over 1 minus 3/5. And then in this series, when n is 0, again, first term is 1, 1 minus 4/5. So what is that? 2/5 flipped is 5/2. And what is that? 1/5 flipped is 5. So we have 5 plus 5/2, or 15/2. So we won't always be able to do that, but this case we could actually give the sum. But any series you have, if you can break it up and the two individual pieces converge, then you know this series converges. Now, what you don't know is if these diverge, it doesn't tell you that the series diverges. And that's what we're going to look at in just a second. Turns out if these both diverge, you know nothing, at least from that. But if one of them converges and one of them diverges, then you do know something. So we will look at that next time.